I have a confession to make right up front. Even the absolute smartest Cambridge Physics 0625 students are making a painful and honestly totally avoidable mistake right now. Look, you're probably spending hours cramming ordinary revision notes, memorizing formulas, reading textbooks cover to cover, but you're completely ignoring the fact that the practical paper doesn't just test your memory, it tests your ability to hack the examiner's mark scheme. Welcome to this explainer. Today, we aren't just studying. No, we are going to legally steal those marks.
Let's hit the ground running with a high-stakes practical exam question that most students get just slightly wrong under pressure. Here it is. Why must you switch off the circuit between your current and voltage readings? Think about it for a second. What's your immediate gut reaction answer? If your first instinct was to say something like, oh, so the wires don't overheat, well, you just lost. Vague answers to this single, incredibly common question will instantly cost you 2 easy marks. And in Physics 0625, 2 marks can literally put your target grade boundaries at risk. There's no margin for error here. All right, Section 1, the practical exam trap. Here's the thing. Relying on basic textbook memorization completely fails in practical papers. The examiner isn't looking for general knowledge. They are looking for specific, real-world scientific reasoning based on the actual constraints of the experiment in front of you. Based on their official guidance, ordinary revision completely ignores these fatal errors. Missing units in your data tables, rounding way too early in calculations, giving those vague safety explanations we just talked about, messing up graph axis scales, and offering really weak practical improvements. If you don't actively bypass these specific traps, you are just leaving marks on the table. Let's fix that. Section 2, the mark scheme heist framework. To consistently secure those top band marks, you need to think exactly like an examiner, and you do that using this simple 4-step framework. Step 1, identify the underlying concept. Step 2, locate the evidence or data. Step 3, apply strict scientific reasoning. And finally, Step 4, translate all of that into exact examiner wording. By following this exact sequence, you transform a basic instinctual guess into an unbreakable, top-tier response. It's a game changer. Moving to Section 3, apparatus and measurement strategy. You have to listen to this direct warning straight from the Cambridge syllabus materials. They explicitly state, if you substitute equipment, consider the accuracy. It is usually much lower than the equipment suggested. So what does this mean for you? Well, if a question asks about substituting an automatic timer with a manual stopwatch, you can't just write, it's different. You must explicitly state that human reaction time drastically lowers the accuracy. You have to write down that specific consequence to actually get the mark. Now, in just a moment, I'm going to show you the one calculation habit that instantly obliterates your marks in a volume and density question. It completely ruins your final answer. But first, we need to apply our framework to make the examiner's safety clues incredibly obvious. Let's dive into Section 4, translating safety into marks. Safety is not just common sense. It requires exact scientific reasoning. Writing "be careful" or "don't get hurt" is never, ever a valid answer on a Cambridge paper. Working with heavy weights, you don't say "don't drop it." You write "always wear shoes so feet are protected if a heavy weight falls." Using large currents, you state set power to a low output and switch off between readings because large currents cause burns, electric shocks, and damage sensitive meters. Working with a mercury thermometer, you have to specify that mercury is a toxic material requiring care to prevent rolling and breaking. Notice the precision there. And the pattern continues across the board. Lasers or UV lamps, you write protect eyes from radiation. Setting up electrical circuits near water or sinks, keep away from taps to prevent electric shocks. Dealing with hot liquids, set in a safe position to prevent burns. It is always hazard plus consequence. That is the formula for how you secure full marks. Section 5, spot the fatal error. Let's apply our 4-step framework to a real scenario. I want you to put on your examiner hat for a second. Look at this flawed student answer. Turn it off so it doesn't get hot. This is exactly what costs you those 2 marks we discussed at the very beginning of the explainer. It totally lacks scientific vocabulary. But look at the top band answer. It hits completely differently. Switch power off between readings because large currents cause burns and damage sensitive meters. Boom. That nails the concept, the reasoning, and the precise examiner wording. Night and day difference, right? Section 6, resolving the density trap. Okay, it's time to close the loop on that calculation error I warned you about earlier. To avoid absolutely destroying your density and volume calculations, you have to follow these absolute rules. First, Always, and I mean always, include the correct units in your final answer, like grams per cubic centimeter. Second, never round too early in multi-step equations. If you round a number in step 1, your final answer in step 3 is going to be completely inaccurate. Keep the full value in your calculator the whole time. And third, ensure your final conclusions are fully supported by the raw data in your table. If your data doesn't explicitly back up your claim, the examiner gives you 0 marks for the conclusion, no matter how good your physics sounds.
Section 7, the Heist Escape Tunnel.
So we've successfully navigated the apparatus and safety heist. You now know exactly how to legally steal marks by using precise examiner wording instead of vague, generalized guesses. But I have to warn you, there's a new incoming threat. What if your practical data has a massive anomaly? What if you sit down to plot your results and you suddenly realize your graph axes and scales are completely, horribly wrong? These graphing errors will instantly tank your grade, and the framework we just discussed needs a serious upgrade to fix it.
The correction sequence continues in the next explainer. This unresolved graphing problem is the absolute mandatory next step to complete your exam strategy. You literally cannot walk into that exam hall without knowing how to handle anomalous data and axis scales.
If you walked into the exam hall right now, would your graph cost you a letter grade? Don't leave it to chance. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. Catch you in the next explainer.